Welcome to NovaSleep. Before you fall asleep, imagine this. Beyond your room, beyond your breath, space itself is moving. Galaxies are drifting apart in perfect silence, stars are dying, and new worlds are being born in the dark. Yet here you are, inside that same cosmic pulse, small but eternal, made of the same particles that glow in distant nebulae. Tonight, you're not just listening to facts, you're crossing the quiet border between knowledge and wonder. Stay with me long enough and the universe will begin to whisper its secrets, one calm truth at a time. By the way, if you like and subscribe to my video, this is the most effective way to support me. If you also write where in the world you are watching and what time it is, I love to read it in the comments. 1. The atoms in your body were born inside ancient stars. Your bones and the blood carry elements that were forged in stellar furnaces long before the sun existed. Hydrogen and helium arrived from the earliest moments of the universe, but the calcium in your teeth, the iron in your hemoglobin, and the oxygen you breathe were cooked in the hot hearts of massive stars. When those stars ended their lives, they scattered enriched matter into space in gentle winds and explosive bursts. That ash drifted for ages until gravity gathered it into new clouds. Within those clouds, tiny grains of dust floated like seeds, each one a nucleus around which gas could condense. Over millions of quiet years, those seeds collected more material, cooling, fragmenting, and darkening into dense knots. In one corner of a spiral arm, a knot collapsed just enough to ignite a new star. Around that young star, a rotating disk of leftovers spun slowly, laced with all the elements made in earlier generations of suns. From that disk, pebbles became boulders and boulders became embryo worlds. Collisions were frequent at first, but time smoothed the chaos into orbits. Minerals fused, water arrived with icy messengers, and the new planet's crust settled. The ingredients once trapped in long-vanished stars found a home in rock, ocean, and atmosphere, quietly waiting for chemistry to become biology. When life finally stirred, it used what the stars had given. Carbon formed the backbone of complex molecules, phosphorus stored energy in living cells, and iron carried oxygen to feed motion and thought. To lie down and rest is to share a lineage with constellations, to feel that every breath is part of a cycle older than mountain. The universe is not far away, it is within you, returning to itself with each heartbeat. 2. Light from distant galaxies began its journey before Earth existed. Look up and you are looking backward in time. The nearest stars show you scenes from years ago, while the faintest smudges in a dark sky are ancient cities of light whose first photons left when the universe was young. Those photons crossed expanding space, their wavelengths stretched into redder colours by the growth of the cosmos. By the time they reach your eyes, they carry quiet messages from an era when our planet had not yet formed. This makes the night sky a record rather than a mirror. Every galaxy's glow arrives with a date embedded in its colour and brightness. Astronomers read that date the way archivists read handwriting, retrieving distances and ages from delicate patterns. The farthest known galaxies send whispers that began shortly after the first stars pierced the cosmic fog, when chemistry was simple and structures just beginning to assemble. The fact of such travel is soothing. Light is patient beyond measure, willing to cross gulfs without complaint, unhurried by the emptiness. It threads past clusters, skirts dark lanes of dust, and slips along the subtle curves carved by gravity. Its persistence means that nothing luminous is entirely lost. Given a clear night and a calm mind, you can receive a signal that has wandered for billions of years. When you close your eyes afterward, some of those photons have been absorbed by the cells in your retina, their energy translated into the language of vision. They are gone as light, yet remain as memory. Your quiet moment has become part of their journey's end, and their journey has coloured your moment. The universe and your awareness meet there, and the meeting is gentle. 3. Time flows differently near massive objects. Imagine a clock resting on a mountain and another at sea level. The one higher up ticks a little faster. Gravity pulls on time as well as on stones, making intervals lengthen or shorten, depending on how deep they sit in a gravitational well. The effect is small near Earth, but grows near heavier bodies. Close to a neutron star or a black hole, minutes and hours stretch like soft metal. This is not a trick of instruments, it is the geometry of the universe revealing itself. Mass tells space how to curve, and curved space tells time how to pass. Light beams climb out of gravity like hikers climbing a slope, losing energy and reddening as they go. The rhythm of atoms slows in deep potential, and the very idea of a universal clock becomes a story we tell for convenience. For daily life, you need not notice. Satellites that guide navigation correct for the difference, or they would drift from accuracy within hours. Pilots do not feel years lengthen as they fly, and ocean tides do not seem to change with the ticking of timepieces. Yet the principle is always there, shaping orbits and the pathways of light, painting a subtle gradient across the world. To rest beneath a night sky is to rest within that gradient. Your heartbeat, your breathing, your thoughts all occur inside a tempo set by where you are and what surrounds you. Somewhere else, another observer experiences the same universe at a slightly different pace. There is comfort in that flexibility. Time is not a rigid cage. It is a soft field that adapts to presence. 4. Space looks gaunt, yet it trembles with invisible waves. Between stars, the vacuum appears void, but it is alive with ripples. Magnetic fields rise and fall, radiation pressure nudges dust grains. Rarefied gas carries long, slow waves that can travel for light years. Even the fabric of space responds to distant motions, passing along gravitational waves when massive objects whirl together. These are not sounds in air. They are patterns in fields, graceful changes that pass without friction. Some of these waves come from the sun. The solar wind carries fluctuations that brush past Earth and continue outward, touching planets and moons, filling the heliosphere with a constantly changing texture. Others originate deep in the galaxy, emitted by stellar births and deaths, or by the dance of compact objects. They stack and cross and fade, a chorus that needs careful instruments to hear. When detectors listen with enough patience, they convert those patterns into data that can be rendered as hums and chirps. A black hole merger becomes a brief rising tone. A pulsar turns into a steady beat. Most of these signals sit far below the threshold of human hearing, yet the mind can imagine them as a soft ocean swell rocking a ship at night. The image is not literal, but it is helpful. It gives the emptiness a rhythm. As you relax, consider that your body feels something similar on a smaller scale. Heart rhythms and brainwaves come and go in quiet cycles, sometimes faster, sometimes slower, each riding on top of the other. Space behaves that way too, with overlapping frequencies and drifting amplitudes. The universe does not shout, it breathes. 5. The night sky is a library of the past. Each point of light is a page written at a different time. Nearby stars describe recent chapters, while dim galaxies conserve paragraphs from early epochs. The arrangement is not random. Constellations are the pattern your culture draws, but behind them lies a deeper structure built by gravity. Clusters are bound families. Filaments are highways of migration. Voids are the wide margins between chapters. Reading this library requires patient methods. Telescopes collect photons for hours to gather enough signal. Spectrographs break the light into bands to reveal composition and motion. Catalogues become indexes that allow cross-referencing between objects near in the sky but far in distance. Over decades, data sets grow into atlases. The atlases become narratives about how stars form and fade, how gas cycles, how galaxies evolve. You do not need equations to appreciate the quiet order. The same physics that organizes a cloud into a star also organizes many stars into a spiral and many spirals into a web. The repetition is not dull. It is musical, a theme with variations across scale. The tune changes with environment and time, but the rhythm is recognizable once you listen for it. When you step outside at night and let your eyes adjust, you borrow a card from that library without leaving a mark. You are allowed to read in silence, to take in a small selection, to put it back when you grow drowsy. The stars will still be there, keeping their places, even as their light ages. The library remains open, and admission is always free. 6. Stars can pulse like slow cosmic heartbeats. Some stars breathe. They expand and contract on regular schedules, brightening and dimming as their outer layers move. The changes are not frantic, they are measured, sometimes taking days or weeks for a complete cycle. These variables are not unstable in a dangerous sense. They are stable enough to keep time, and astronomers use them as distance markers across vast tracts of space. The cause is a balance between pressure and gravity. As a star swells, its outer layers cool and become more transparent, letting energy escape. Losing energy makes the star contract again. Contraction heats the layers and increases opacity, trapping more energy until the star swells once more. The result is a loop, steady and characteristic of a star's temperature and composition. From far away, such a star seems to tap its own surface with a soft drum. The brightness curve looks like a smooth wave. When many of these stars are found in a cluster or a nearby galaxy, their pulses can be calibrated into distances. In this way, gentle stellar breathing helped us build the first accurate scale of the universe beyond our home galaxy. There is a lesson in the pace. Nothing living or luminous keeps a perfectly fixed output. Regulation comes from feedback, and feedback requires change. Stars teach that even steady light is maintained by motion beneath the surface. What you see as calm is often a balance of opposing forces that have learned to share space. 7. The colour of a star quietly reveals its life. To the eye, it's just a range from blue-white to orange-red. Those colours are not cosmetic. They are thermometers. Blue stars burn hot and spend their fuel quickly, living bright, short lives. Redder stars are cooler and last much longer. Between them lie the yellow and white middle types, including the Sun, which balances output and lifetime in a gentle compromise. Spectra add detail to the story. When starlight is spread into its rainbow, dark lines appear where atoms absorb specific wavelengths. Those lines identify elements and trace conditions in the atmosphere. They also shift slightly when a star moves toward or away from us, letting motion be measured from afar. With time, a portrait emerges that includes age, mass, chemistry, and speed. Patterns in stellar colour across a cluster create a diagram that acts like a family photograph. Hot young members crowd one side, while cooler elders occupy another. The point where stars peel away from the main trend reveals the cluster's age. By comparing many clusters, astronomers reconstructed how stars change from infancy to old age, and how they end as white dwarfs, neutron stars, or black holes. When you notice a warm orange spark near the horizon, or a cool blue pinprick higher up, you are witnessing biography written in light. The sky is full of such biographies, each burning according to its resources and environment. Diversity is not noise, it is information, and beauty is part of how the information arrives. 8. Space between galaxies holds a hidden energy. Galaxies drift apart faster than gravity alone would predict. The simplest description is that empty space itself carries an energy that pushes on the cosmic fabric. This energy does not gather into clumps or form stars. It is smooth and persistent, a quiet pressure that reveals itself only on the largest scales. We call it dark energy because it does not shine and because it is still partly mysterious. Evidence comes from multiple routes that agree. Supernova distances plot a curve of expansion that bends upward. The pattern of galaxies across the sky shows preferred scales that fit a universe with this extra push. The oldest light carries tiny temperature variations that reflect the same story. When independent measurements converge, confidence grows, even if the mechanism remains to be clarified. For your nightly peace, the details can soften into a simple image. Imagine the universe as a fabric on a gentle loom, and dark energy as the steady motion of that loom's frame. Threads lengthen over time, patterns stretch. No single star or planet notices the immediate tug, but the whole tapestry slowly widens. The process is not violent. It is patient. Sometime far ahead, the result may be isolation. Local groups of galaxies remain bound, but distant ones slip beyond observability. Night skies in that era will look quieter than ours. Yet the memory of connection will exist in records, and the laws that permitted it will still apply. Expansion is a kind of breath on the scale of everything. 9. There are more stars than grains of sand on Earth. The comparison is not exact, but as an image it helps the mind step into immensity. Count the beaches and deserts, count every grain, and then consider that the universe likely holds even more stars. Many are dim red dwarfs that would go unnoticed to the unaided eye. Many are hidden behind dust or too far away to resolve. They exist all the same, each with a potential retinue of worlds. This abundance changes the way we think about rarity. If a rare event has a chance to occur around one star in a million, and there are trillions of stars, then rarity becomes common somewhere. Planet formation, once an idea, is now observed in disks around young stars. Planets are counted by the thousands. Some orbits are tight, some are wide, some eccentric, some tranquil. Variety is not a surprise anymore. If you feel small in this context, remember that small and precious can be the same idea. A grain of sand can hold a fossil ripple of a long, vanished wave. A star can host a world where minds consider stars and sand together. The great and the tiny belong to the same whole. 10. The universe expands as you breathe. Between one inhalation and the next, the scale of the cosmos increases by a fraction too small to sense. The increase is everywhere at once, not a movement through space, but a growth of space. Nearby things remain bound by forces stronger than the expansion, so your room does not inflate and your body does not stretch. The change shows itself only across distances where gravity relaxes its grip. To know this is to accept a subtle rhythm that cares nothing for haste. Astronomers measure it with standards that stay consistent over long times, comparing the brightness of known candles and the shapes of galaxy spectra. They argue about exact numbers, so refine methods, and revisit assumptions. The debate is part of the work, and the work slowly sharpens a picture that spans billions of years. There is a comfort in living inside a process that continues regardless of concern. Seasons turn, stars evolve, galaxies drift apart. None of these demand effort from you, yet you are permitted to notice and to understand. Understanding does not spoil the poetry. It provides meter and rhyme, making the verses easier to remember. As you settle into rest, you can let the image of expansion soften into a feeling of spaciousness. Thoughts that seemed crowded find room. Worries that felt tight loosen slightly. The universe makes space by nature. You can allow a little of that nature to arrive in your breath. 11. Quantum fluctuations never truly rest. Even in a perfect vacuum, fields flutter faintly. Virtual particles appear and vanish within intervals allowed by the uncertainty of energy and time. They do not become permanent matter without help, yet their brief lives add up to measurable effects. They shift energy levels in atoms and influence how light travels through emptiness. Stillness, at the most basic level, contains activity. This constant low murmur is not chaos. It is statistical, governed by rules that have been tested many times. The average value might be 0, but the fluctuations around that average are real. In some theories, the early universe amplified such tiny variations into the seeds of galaxies. A whisper became a structure by slow gravitational growth, and the shape of the sky today remembers that origin. You can adopt a parallel for your inner life without forcing it. Beneath calm surfaces, the mind moves. Thoughts arise and fade, often without becoming action. They leave traces that choose later paths, nudging attention here or there. Calm does not mean emptiness of content. It means acceptance of gentle motion without grasping at each ripple. This way of seeing reduces the urge to fight small disturbances. A passing idea can pass, a small sensation can be allowed. The vacuum never stops fluctuating, and yet the universe remains coherent. Your rest can include motion at the smallest scale and still be rest. 12. Some planets complete a year in mere hours. Close to their stars, a few worlds race around in orbits so tight that a full circuit takes less than a day. Their skies change rapidly. Temperatures sweep from blistering day to shadowed night across narrow boundaries, and their atmospheres, if any survive, are sculpted by intense radiation and tides. These are not destinations for life as we know it, but they demonstrate how flexible planetary systems can be. Such planets often form farther out and migrate inward through interactions with disks or with companion worlds. Their migration stops where forces balance, sometimes just above the star's surface. Observers notice them when they transit, creating tiny dips in starlight that repeat at precise intervals. The regularity becomes a clock. The depth of the dip hints at size. The shape of the curve reveals atmosphere or clouds. Recognizing this breadth takes pressure off narrow expectations. There is no single correct way for a planetary family to arrange itself. Stability can be found in many patterns. Your life can acknowledge the same principle, allowing different calendars and rhythms to remain valid as long as they hold together without strain. 13. Neutron star matter is unimaginably dense. If you could hold a teaspoon of material from a neutron star, it would outweigh mountains. Protons and electrons are crushed together under gravity to form a city of neutrons, packed so tightly that quantum rules provide the only resistance against further collapse. The surface is a crust of exotic nuclei, a sea of near-pure neutrons. Below that, the density climbs toward the threshold where a black hole would form. Neutron stars spin rapidly and carry magnetic fields of staggering strength. When their beams sweep past Earth, we notice them as pulsars with millisecond precision. Some pairs spiral together over millions of years until they emerge, releasing gravitational waves and a burst of heavy elements. Gold and platinum may owe much of their cosmic abundance to those rare collisions. The existence of such objects shows how far matter can be pushed while remaining matter. It also connects gentle observations to fierce processes. A slight tick in radio timing implies a star under pressure harder than anything on Earth. A small wiggle in a gravitational wave detector implies a catastrophe that briefly outshines galaxies. In the quiet of a bedroom, contemplating such extremes can paradoxically soothe. The universe contains and survives them. Spikes of energy rise and fall, but overall the cosmos continues its slow work. Knowing that allows you to let go of smaller spikes in your own day. 14. Galaxies can collide in graceful slow motion. When two islands of stars approach, their stars seldom crash. The distances between stars are so vast that they pass like flocks interleaving. What changes is the shared gravitational field. It pulls out long tidal tails, bends disks into bridges, and funnels gas towards centers where new stars ignite. Over hundreds of millions of years, two shapes become one, remixed but not destroyed. Such events are common in the universe's history. The Milky Way itself shows scars of past encounters, and in the far future it will meet Andromeda and reshape into a new form. Simulations visualize the dance, turning equations into moving pictures that match what telescopes observe. The agreement suggests that gravity, given enough time, writes with a consistent hand. Mergers can feed central black holes, lighting active galactic nuclei that blaze across space also. They can also quench star formation by heating gas beyond the point where it can cool and collapse. Outcomes depend on angles, masses, and amounts of gas, with small differences leading to different results. There is no single script. There are families of possibilities. If your day felt crowded with near misses, remember that crowds can pass through each other without harm when the spacing is right. Motion can be complex without being destructive. Patience is the main ingredient. On a galactic scale, patience is measured in eons. On a human scale, it is a few breaths. 15. The vacuum is not empty at all. Take away air, dust, and light, and what remains still holds fields that permeate space. Quantum electrodynamics and related theories describe how those fields fluctuate and how they interact with particles. Effects like the Casimir force arise when boundaries restrict fluctuations, producing a tiny but measurable attraction between plates placed very close together. Emptiness acquires texture. In cosmology, the energy of empty space plays a role in expansion. Whether it is constant or slowly changing is an open question, but in either case it demonstrates that nothingness can have properties. The old metaphor of space as a stage, waiting for actors, gives way to a newer picture where the stage participates in the play, responding to mass and energy and feeding back into motion. This idea can feel unsettling until it becomes familiar. We are used to thinking of the background as inert. Learning that the background has a character changes the questions we ask. It suggests that even the quietest conditions carry potential. It reframes the boundary between something and nothing. For rest, it offers a simple comfort. You do not need to fill every moment to have value. An empty evening contains structure. Unscheduled time holds possibilities that manifest when conditions are right. The vacuum teaches that potential can be present without display. 16. Some black holes spin and drag space around them. Rotation twists the nearby geometry so that space itself is pulled along. This frame dragging means that anything falling toward the hole must co-rotate to some degree. The effect creates an ergosphere outside the event horizon, where energy abstraction becomes theoretically possible. Jets that blaze from the poles of active galaxies likely draw power from magnetic fields threading this rotating engine. Observations of light near such black holes show distinctive signatures. Rings appear brighter on the side where rotation boosts photons and dimmer on the opposite side. The size of the shadow tells mass. The surrounding glow tells about spin and feeding. With careful modelling, images sharpen into measurements, and measurements into physical stories. Spin also affects the growth and alignment of black holes within galaxies. Mergers can flip axes. Accretion disks can torque central objects over time. The evolution of spin becomes a diary of past meals and encounters. Reading that diary requires patient comparisons between theory and observation, a slow conversation across wavelengths. As an image for the mind, imagine a whirlpool whose water drags twigs along even before they reach the visible current. The twigs are stars and gas, the water is space-time, the pull is strong near the centre and fades with distance. Knowing this, you can picture how motion and gravity weave together without straining for metaphors that do not fit. 17. Gravity bends light into delicate arcs. A massive cluster of galaxies can act as a lens, curving the paths of passing photons and stretching background galaxies into thin arcs. Sometimes the alignment is precise enough to create multiple images of the same source or a near-complete ring. These lenses serve as natural telescopes, magnifying distant objects that would otherwise be too faint to study. By mapping how background images distort, astronomers infer the distribution of mass in the lens, including mass that does not emit light. Dark matter reveals its outline through the geometry it imposes. The method complements other approaches, and together they build a consistent case that most mass is not in stars or gas. The sky becomes both scene and instrument. On smaller scales, individual stars can lens background stars in brief brightenings, called micro-lensing events. These events have discovered planets that do not transit, and are too far for other techniques. Each brightening is a reminder that the line between observer and observed is shared by gravity, which treats light as it treats stones, guiding paths along curves. As you prepare for sleep, consider how a path can be altered without the traveller noticing the cause. Light does not resist bending. It follows the easiest route through curved space. Sometimes that is the best strategy in life as well. Accept the gentle curve and you will still arrive. 18. The cosmic microwave background is the universe's oldest light. It fills all directions with a faint glow that peaked when the universe was young and hot. As space expanded, the glow cooled and stretched into microwaves, becoming a nearly perfect black-body spectrum with tiny variations. Those variations are the imprints of early density differences, the seeds from which galaxies grew. The map of this glow is a baby picture of everything. Measuring it precisely required instruments above the atmosphere, where water vapor does not absorb microwaves. Missions built over decades improved resolution and sensitivity, turning a uniform field into a detailed pattern. The pattern encodes parameters like the age of the universe, the amount of matter and dark energy, and the geometry of space on large scales. The success of this approach demonstrates how quiet signals can carry loud meaning. A small temperature difference recorded across the sky becomes a set of numbers that define our best model. The model may adjust with new data, but its backbone comes from this diffuse light that asks for nothing more than patient listening. The comfort here is twofold. First, that the universe has a memory and keeps it without effort. Second, that clarity arrives from softness. No single bright point provides the answer. The whole field does, gently. 19. The early universe was a glowing fog. Before atoms formed, free electrons scattered light, keeping space opaque like a bright mist. As expansion cooled the gas, electrons settled into orbits around nuclei and the fog cleared. Photons began to travel freely, creating the background just described. This recombination was not sudden everywhere at once. It progressed as conditions allowed, leaving subtle signatures into the pattern of ancient light. Afterward, darkness returned until the first stars kindled. Their ultraviolet light rayonized hydrogen in their neighborhoods, carving bubbles of transparency that grew and overlapped. The cosmic dawn turned a foggy scene into a structured one, with light escaping along new corridors. Observing this epoch is difficult because it sits at extreme distances, but new instruments are beginning to capture hints of it. Understanding these transitions helps explain why the universe looks the way it does now. It clarifies the timing of star formation and the way matter collected into halos. It connects simple beginnings to complex outcomes in a chain that respects cause and effect while allowing for chance. As a reflection, fog dissolving into clarity is a familiar image. Morning mist thins. A crowded mind settles. Shapes appear where there was only brightness. The story of the sky and the story of a day share that motion. 20 down to supernovae forge the gold we wear. When massive stars exhaust their fuel, their cores collapse and their outer layers rebound in an explosion that floods space with neutrons. In that environment, heavy elements assemble rapidly, including gold. Some of this forging also occurs when neutron stars merge, but supernovae remain a principal factory. The products mix into clouds that later form new systems, embedding gold into planets and eventually into hands. Astronomers trace this origin by examining the spectra of old and young stars. Older populations show fewer heavy elements, while newer ones display richer signatures. The trend maps a chemical history of the galaxy, a record of enrichment through repeated cycles of birth and death. In some regions, the process is fast, in others, it is slow. The balance depends on environment and time. Knowing where elements come from changes how they feel. A ring or a circuit is not merely a product of industry, it is a fossil of a stellar event, a durable token of a brief extreme. To wear it is to carry a reminder that violent moments can leave gifts when viewed across the right span. This does not romanticize destruction, it places it into context. Stars do not explode to make adornments, they end because physics requires an end. Out of that necessity comes a supply of building blocks that life and culture can use. The cosmos wastes little. 21. Every large galaxy hides a central black hole. At the hearts of massive galaxies, gravity collects matter into compact objects whose presence is betrayed by the speeds of nearby stars and the radiation from accreting gas. These central black holes grow with their hosts, regulated by feedback that can either promote or suppress star formation. The correlation between black hole mass and galactic bulge properties suggests a long partnership. When gas spirals inward, it heats and glows across the spectrum. Some of that energy launches jets that puncture the surrounding medium. The jets can travel far beyond the galaxy, stirring the intergalactic environment. Over time, such activity maintains a balance that prevents runaway cooling or heating, keeping systems near a state where structure can persist. Quiet periods are common. Not every center blazes. Many sit dormant, having eaten recently or lacking fuel. Dormancy is not absence. The black hole waits, altering orbits simply by existing. Patience is part of its nature, and scale grants it the time to be patient. You're not likely to see the one in our own galaxy directly, but its influence shapes motions near the core. The image captured out of its shadow is a kind of proof through silhouette. A dark circle against a blurred glow is enough to say that the center holds. 22. Pulsars sweep like precise lighthouses. A pulsar is a rotating neutron star whose magnetic axis is tilted from its spin axis. Beams of radiation emerge from the magnetic poles and sweep the sky like the beams from a lighthouse. When one of those beams crosses Earth, we detect a pulse with remarkable regularity. Some pulses rival atomic clocks over long periods, enabling tests of gravity and searches for waves from distant happenings. Binary pulses provide especially rich laboratories. Their orbits decay as they radiate energy through gravitational waves, and the rate of decay matches predictions with exquisite accuracy. This agreement builds confidence in the underlying theory, while pointing toward phenomena still to be observed directly. It is satisfying when a simple repeating signal encodes deep physics. Pulsars also host surprises. Glitches occur when their crusts rearrange and suddenly spin slightly faster. Sudden changes in pulse profiles reveal magnetospheric shifts. These departures from regularity remind us that even reliable systems carry internal dynamics that can leap when thresholds are crossed. As a metaphor for bedtime, a steady beacon that rarely falters encourages relaxation. You can let the pulse lead your breath, lengthening the exhale, shortening the worry. A clock in the sky will keep time while you rest. 23. The Milky Way and Andromeda are approaching each other. Over the next few billion years, our galaxy and its neighbour will draw together, pass through one another, and eventually combine. The night sky for future observers will change as Andromeda looms large, then shreds into streams, then settles into a common envelope. Stars will rarely collide, but gravitational tides will reorganize orbits, and bursts of star formation may light new regions. This forecast comes from measuring Andromeda's motion toward us and across the sky. Their speeds are modest in daily terms, but significant over cosmic time. Simulations explore many angles and mass ratios to predict the likely sequence. None of it threatens present life on Earth. The show belongs to distant descendants. Knowing this can feel like hearing about a festival planned ages from now. It is not a call to act. It is a gentle widening of perspective that makes current concerns less sharp. Your world has a place in a larger choreography that proceeds at a tempo beyond urgency. If clouds cover the sky tonight, the dance continues. If the air is clear, it continues. If you are awake, if you're asleep, it continues. Continuity is its nature. 24. Distant starlight arrives stretched by expansion. As space grows, the wavelengths of light travelling through it grow too. Blue slips toward red slides into infrared. The shift carries information about distance and time. By measuring it across many galaxies, astronomers draw a curve that reveals how expansion has changed. That curve is a record of the tug of matter against the push of dark energy. For an artist or a dreamer, redshift is a palette expanded by motion and history. Colours are not fixed labels, they are flexible responses to context. A galaxy's intrinsic spectrum becomes a different spectrum after a long journey. Neither is wrong, both are true within their frames. Instrument builders take advantage of this by designing detectors sensitive to bands beyond human sight. The universe glows brightly in ranges the eye cannot see, and those ranges carry stories of star formation and dust. Translating the invisible into images reveals hidden structures in familiar shapes. Let that be your permission to translate your day into a softer key for sleep. What felt too bright can be shifted toward a calmer tone. The content remains. The presentation changes. The mind responds. 25. The cosmic web threads the universe together. On the largest scales, matter arranges into filaments and nodes that resemble the branching of trees or the wiring of a brain. Gravity pulls along lanes of higher density, while dark energy stretches the lanes apart. Where filaments cross, clusters form. Where they do not, voids open. Simulations began as guesses and grew into detailed portraits that match surveys of galaxies. Gas follows the same structure, heating where it falls in and cooling in quieter stretches. Along the filaments, galaxies draw fresh material and grow. In clusters, interactions strip gas and alter shapes. The web is both scaffold and river network, providing the routes along which evolution proceeds. Seeing it is like lifting a veil and finding the hidden framework of a tapestry. Observations use multiple tracers. X-rays highlight hot gas in clusters. Radio maps reveal faint emissions between them. Gravitational lensing weighs the mass that light does not show. Piece by piece, a multi-wavelength picture emerges, more confident each year. The agreement among methods builds trust in the overall map. For rest, the image offers a suggestion. Complex things often share simple underlying patterns. You do not need to hold every detail in mind to feel held by the structure. Knowing there is a web is enough to lean back. 26. Rogue planets drift through darkness. Between the stars wander worlds without a sun, released from their birth systems by gravitational shoves, or born in isolation within collapsing clumps of gas. They travel in long, cold arcs through interstellar space, unlit and nearly invisible except when their gravity briefly magnifies the light of distant stars. Each one is a complete world that no dawn ever reaches, a planet whose nights are unbroken and calm. Heat within such planets does not vanish entirely. Residual warmth from formation lingers in the core, and radioactive elements release energy slowly over ages. Some may keep underground oceans sealed beneath ice, warmed by the press of rock, the decay of minerals. Life as we know it is unlikely on their surfaces, yet the interiors could stay dynamic far longer than intuition suggests. Astronomers find hints of these travelers through microlensing events when a foreground object bends and brightens the light from a background star for days or hours. The statistics imply that rogue planets may be numerous, perhaps rivaling the count of planets bound to stars. They are part of the galaxy's hidden population, a quiet diaspora that rarely announces itself. To picture a rogue planet is to picture a cathedral of silence. No sunrise to hurry it, no seasons to rush it, only steady motion along a path determined long ago. There is comfort in that kind of constancy, a reminder that a life can continue in peace, even when it leaves familiar orbits. 27. Gravitational waves are ripples in the fabric of space. When massive bodies accelerate together, they send out tiny distortions that stretch and squeeze space as they pass. These ripples are unimaginably faint by the time they reach Earth, changing lengths by less than the width of an atomic nucleus across kilometers. Yet with instruments built to extraordinary precision, the passing waves have been measured, turning a prediction into a listening practice. Most of the signals detected so far come from pairs of black holes and neutron stars spiraling inward until they merge. The last seconds produce a rising tone as energy radiates away and the orbit tightens. Each event carries information about masses and spins, about distances and environments, about how common such pairs are in the universe. Observatories on different continents compare arrivals to locate the source on the sky. A new method is now taking shape that listens to very slow waves, Gs, by tracking arrays of pulsars spread across the galaxy. Subtle shifts in their regular ticks reveal a background hum from supermassive black holes in distant galaxies. Together with the ground detectors, this extends hearing from quick chirps to deep bass notes, building a fuller symphony of cosmic motion. For rest, imagine that symphony as a tide too gentle to feel on the skin yet strong enough to register in careful logs. You do not need to hold the equations to feel the idea. The universe moves and the motion leaves music. You can let the music play while you sleep. 28. The Boutte d'Or. Void is a vast cosmic emptiness. On the map of galaxies, there is a region in the direction of the constellation Boötes where far fewer galaxies appear than average. It is not perfectly empty, yet compared with its size it holds little structure. A bubble tens of millions of light years across where the cosmic web thins. Such voids are a natural part of a large-scale growth that sends matter toward filaments and nodes while leaving broad hollows behind. Surveying these regions refines models of how gravity sculpts the distribution of matter over time. The shapes and sizes of voids depend on the initial conditions encoded in the oldest light and on how quickly structures form. By counting voids and measuring their profiles, astronomers test the same theories that explain clusters and filaments, but from the quiet side rather than the crowded side. Voids are not static. Galaxies at their edges can feel a gentle outward pull as matter slips away along gradients in the density field. Gas within can be warmer and thinner, star formation slower, interactions rarer. The environment shapes the lives of the few inhabitants, giving them histories that differ from galaxies born in busier intersections. The image of a vast hollow can be calming. Space makes room for almost nothing and lets that nothing persist. You can borrow that idea at bedtime. Make room in the mind where few thoughts travel. Let the quiet be a structure, not an abundance. 29. Cosmic rays pass through you every night. High-energy particles arrive from the Sun, from remnants of supernovae, and from even more distant accelerators in other galaxies. Most are protons, some are heavier nuclei or electrons. Earth's magnetic field and atmosphere shield the surface from the harshest effects, but a gentle rain still reaches ground level. It leaves tiny tracks in detectors and even in pieces of everyday material that record impacts over time. Balloon flights and satellites measure the spectrum of energies and the mix of elements in these particles. The pattern tells of shock waves and expanding remnants that fling charged particles to near light speed. It hints at rare events that push a few to energies hard to explain. When a particle strikes the upper atmosphere, it triggers a cascade of secondary particles that spread like an invisible shower. These visitors are part of the background of life on a planet under a star in a galaxy full of energetic processes. They're a reminder that even on quiet nights the world is connected to remote engines. The connection is mostly harmless thanks to layers of protection that function without conscious attention. Knowing this, you can let go of the urge to manage everything. Some protection is built in, some storms pass far away. The mind can rest while the planet does its work. By the way, if you like and subscribe to my video, this is the most effective way to support me. 30. The cold of deep space nears absolute zero. Far from stars and warm dust, the temperature of space approaches the background set by the oldest light, just a few degrees above absolute zero on the Kelvin scale. That is not a room you can visit, but it is a boundary condition that shapes how gas clouds collapse and how molecules form. Cold promotes the sticking of atoms to dust grains where chemistry can proceed along pathways unavailable in warmer places. Regions of intense cold have been found even within our galaxy. Pockets where the glow drops slightly below the average due to peculiar motions or special conditions. In laboratories on Earth, scientists have cooled small samples to temperatures colder than any known place in nature by using lasers and magnetic fields to remove energy from atoms step by step. These achievements open doors to new states of matter and new sensors that can read the world with exceptional sensitivity. For astronomy, cold is both a challenge and an aid. Instruments must be chilled to reduce their own glow when they look for faint signals in the infrared. Space telescopes carry cryogenic systems that keep detectors quiet so the universe can speak. The quieter the instrument, the more detail can be heard from distant structures. To imagine such cold is to imagine stillness that is almost complete. It does not demand that you be rigid. It suggests that motion can slow until the noise falls away. Sleep comes more easily when noise falls away. 31. Hydrogen is the quiet majority of the cosmos. The simplest atom dominates by count across interstellar and intergalactic space. It fills clouds that span light years, streams between galaxies, and feeds the formation of new stars when conditions allow. In its neutral state, it emits a faint radio signal at a wavelength that passes through dust, enabling maps of hidden regions. In its ionized state, it outlines the footprints of recent star formation and energetic radiation. Hydrogen's role in stars is central. Fusion of hydrogen into helium powers the main phases of stellar lives, balancing gravity with outward pressure. The rate of that fusion sets the temperature and luminosity of each type of star. When hydrogen in a core runs low, seas change character, swelling and cooling or contracting and heating depending on mass, beginning the path to heavier elements. Chemistry builds on this foundation. Hydrogen bonds shape water and organic molecules, stabilizing structures that living systems rely on. In space, hydrogen atoms meet on dust grains to form molecular hydrogen, a step that cools clouds and lets gravity gather them more tightly. From simple beginnings grow complex outcomes. There is peace in remembering that the common and the simple sustain the remarkable. No elaborate ingredient is required at the start. A universe made mostly of one thing can still flower into countless forms. 32. The first stars were almost pure hydrogen and helium. After the universe cooled enough to form atoms, there were no heavy elements. The first stars that gathered from that pristine gas were likely massive and short-lived, lighting the darkness with ultraviolet radiation that altered their surroundings. Their death seeded the next generation with carbon, oxygen, and other essentials, making later stars and planets richer in possibilities. Finding direct evidence of those earlier stars is difficult because they burned quickly and far away. Clues come from the chemical fingerprints in very old stars that formed soon after, which show extremely low amounts of heavy elements. Telescopes that can see faint galaxies at great distances now glimpse times when the first clusters were beginning to assemble, adding context to the story. Computer simulations follow the collapse of the first clouds and predict how feedback from the first stars carved the medium. The balance between cooling and heating, between gravity and pressure, determined whether a region would form one giant star or several smaller ones. The details are still being refined as new observations arrive. The arc from simple gas to complex chemistry is long but clear. From near purity came variety, from scarcity came abundance. That is a comforting pattern for anyone beginning again with limited resources. 33. Time may emerge from the quantum world. Some ideas in foundational physics suggest that time as a smooth-flowing parameter might be an emergent description that arises from deeper relations among quantum states. In such views, the feeling of before and after is a large-scale property, like temperature that arises from many molecules rather than belonging to any one molecule. Experiments cannot yet decide among competing pictures, but the discussion sharpens questions about what clocks truly measure. Entanglement plays a role in many proposals, correlating subsystems in ways that create an effective order without requiring an external tick. Thermodynamics also enters since the direction we call forward is linked to increasing entropy in closed systems. If time emerges where correlations and entropy behave in certain ways, then different regimes of the universe could exhibit different senses of time or none at all. This is heady territory, yet it bears on calm. If time is not a rigid river, but a pattern that appears when conditions are right, then our experience of its pressure can soften. The seconds on a clock remain useful, but they need not dominate the inner narrative. Waiting becomes less harsh when the yardstick itself is seen as a tool rather than a law. At night, that tool can be put down, the breath can become the only metronome you need, and even that metronome can slow without losing meaning. Whatever the deepest story, rest is permitted within it. 34. White holes are a speculative mirror to black holes. In equations that describe black holes, there exist solutions that look like time reversals where nothing can enter and matter can only emerge. These hypothetical objects are called white holes. No observation has confirmed their existence. They serve as thought experiments that test how far current theories can be stretched and what constraints nature imposes on extreme ideas. Some researchers have explored whether the interior of a black hole could transition to a white hole phase under quantum effects, potentially releasing information in a late, gentle trickle rather than swallowing it forever. Others argue that the environments required are not realized in our universe, or that instability would prevent formation. The debate clarifies what we mean by horizons, evaporation, and information. Even if white holes never exist in nature, they help frame questions about singularities where classical descriptions fail. They motivate searches for a synthesis between quantum theory and gravity that removes infinities and replaces them with finite processes. Progress may come indirectly through precise observations of black hole shadows and gravitational waves that restrict what is possible. Speculation can be restful when it is held lightly. You do not need to choose a side. You can let the mind play at the border of the known, then return to the certainty that stars still rise and set in the same reliable way. 35. The observable universe has a horizon we cannot cross. There is a limit to how far we can see because light has had only a finite time to travel since the beginning of expansion. Beyond that distance there may be more of the same or something different, but no signal from there has reached us yet. The horizon is not a wall, it is a moving boundary that shifts as time passes, letting more regions come into view while others recede in terms of causal contact due to accelerating expansion. This horizon shapes what questions can be answered with observation. Cosmology builds models and tests them against what fits inside our light cone. Assumptions about what lies beyond are checked by consistency. If a model predicts patterns we can see and explains phenomena across scales, confidence grows that it remains valid outside our current reach, though humility remains wise. The existence of a horizon is a gentle limiter. It says that not all mysteries are available at once. Patience and a method are part of the craft. Instruments improve, surveys deepen, and the circle of the known widens without needing to be complete. For sleep, horizons are helpful images. You can let the day end at its own horizon. What lies beyond can wait for morning. The boundary is not a failure. It is a promise that discovery has a tomorrow. 36. Galaxy clusters are linked by invisible filaments. Across the deep sky, the most massive gatherings of galaxies do not float alone. They sit at the crossings of long, faint bridges of matter that stretch for tens of millions of light years. These bridges are made mostly of dark matter, with a thin garnish of gas, too diffuse to shine brightly yet heavy enough to guide the motions of entire clusters. Surveys that map weak lensing reveal their outlines as gentle distortions in the shapes of thousands of background galaxies. Along these filaments, gas flows like a slow river. As it streams inward, it heats through compression, lighting up in X-rays where it becomes dense enough. Galaxies riding these currents pick up fresh fuel that can feed new generations of stars. Where filaments intersect, the supply increases, and clusters grow faster, building towering stacks of galaxies bound by a shared gravity well. The pattern began with tiny ripples in the early universe. Gravity amplified those ripples unevenly, pulling matter toward the slightly denser lanes and away from the slightly emptier gaps. The result is a scaffold that looks strangely familiar, with branching strands that resemble neural tissue. The similarity is a coincidence of mathematics rather than a sign of kinship, yet it helps the mind accept scale without fear. To contemplate these links is to feel steadied by structure. The universe is not a scatter of isolated islands. It is a connected landscape where growth follows pathways and where emptiness and fullness cooperate to shape what forms. 37. Light behaves as both wave and particle. When light spreads through a slit, it makes bands that only waves can make. When it strikes a metal surface and knocks out electrons, it reveals itself as packets of energy that only particles can explain. The two faces are not a contradiction. They are a complete description woven into a single entity called the quantum of the electromagnetic field. Which face appears depends on which question is asked. Experiments push this dual nature to the edge of intuition. Single photons can interfere with themselves when allowed two paths, building a pattern one dot at a time. Detectors that try to record which path the photon took erase the pattern and replace it with a simpler distribution. Information and outcome turn out to be entangled companions rather than independent strangers. This strange loyalty to context is not limited to light. Electrons, atoms, and even large molecules display wave habits when conditions are quiet and controlled. As systems grow and interact with their surroundings, their wave features blur into classical behavior. The world appears solid because constant contact keeps quantum possibilities from remaining sharp. The lesson is gentle. Nature is richer than any single picture. When a simple image fails, another can step in without hostility. Calm arrives when the mind allows more than one frame to be valid and lets evidence choose which frame to use. 38 entangled particles act as if distance is irrelevant. Prepare two particles so that their properties are linked, then separate them by a wide gulf. Measure one and a pattern appears in the other that matches the link, no matter how far apart they travel. No usable signal outruns light, and no message rides this link. Yet the correlations defy any story in which the particles carried fixed instructions from the start. The universe agrees to outcomes in a way that does not fit everyday separations. Tests of this behavior have closed loopholes one by one, using fast switches of measurement settings and large separations to prevent hidden communication. The results point toward a reality where relations carry as much weight as individual properties. What exists is not only things, but also the connections between things, written into the mathematics as shared states. Entanglement is not fragile by nature. It can be distributed, purified, and even used as a resource in emerging quantum networks. Devices that sense tiny fields, clocks that keep time with astounding fidelity, and proposals for secure communication all lean on this odd linkage. The frontier is practical as well as philosophical. To rest with this idea is to accept that closeness has more meanings than meters. Bonds can persist across distance without drama, quiet and reliable, asking only that the environment remain gentle enough to avoid random interruptions. 39. The universe might be spatially flat on large scales. Measurements of the oldest light and of the layout of galaxies indicate that, averaged over enormous distances, space does not curve much, one way or the other. Straight lines stay straight and triangles add to nearly 180 degrees. This is an average statement, not a denial of local curvature near massive bodies. Hills and valleys exist, but the panorama looks level. A flat geometry carries implications for the contents and past of the cosmos. It suggests a balance between mass energy and the rate of expansion that early processes helped arrange. Inflationary models explain this balance by stretching any initial curvature toward flatness in a brief, rapid growth spurt long before stars formed. Observations have tested many predictions of that idea and found close agreement, while still leaving room for refinements. Flatness does not mean sameness. Structure is rich and varied. What flatness gives is a simple background rule over which complexity can unfold. Distances scale in predictable ways, and light travels according to equations that match data across multiple methods of measurement. Confidence grows when independent routes converge on the same quiet conclusion. Equilibrium at grand scale can be a calming image. The ground beneath a busiest city may be rough in detail, yet the horizon looks steady. A balanced backdrop allows intricate lives to proceed without losing bearings. 40. Some exoplanets may rain diamonds. On worlds with thick atmospheres rich in methane, and with crushing pressures in their deep layers, carbon can break bottom free and condense into solid forms. Laboratory studies suggest that within such conditions, carbon may crystallize and fall as glittering precipitation toward hotter depths, where it might melt again into oceans of dense fluid. The cycle would be exotic and relentless, running without any need for sunlight. Giant planets in our own system hint at these possibilities. Neptune and Uranus hold compositions where carbon is plentiful, and experiments that simulate their interiors see diamond formation at relevant pressures and temperatures. For planets around other stars with even more extreme conditions, the process could be stronger, producing layers rich in crystalline carbon that flow and remix over ages. Such weather is not a promise of habitability, it is a sign of exuberant chemistry when gravity and composition meet. The picture expands the catalogue of what a planet can be, moving beyond rocky spheres and gas balls to include materials and phases that challenge common sense. Variety is not decoration, it is the default outcome of broad possibilities. Thinking about this rain is oddly soothing. The universe hosts beauty that nobody sees, repeating patterns that continue whether or not eyes are present. Quiet cycles can be complete in themselves. 41. Spacecraft like Voyager travel beyond the solar wind. Launched to tour the giant planets, the Voyager craft kept going after their encounters, and eventually cross the boundary where the sun's outflow gives way to the subtle pressure of the interstellar medium. Instruments still sip power from long-lived generators and send home packets of data that chart density, magnetic fields, and endocosmic rays far from home. The signals are faint and tardy, yet they arrive. These craft carry golden records with sounds and images from Earth, chosen as greetings for anyone or anything that might find them. The gesture is more poetry than plan, yet the presence of those records helped define the mission as a human project rather than purely a technical one. Messages ride on machines that continue to function long past their original script. Crossing the boundary known as the heliopause revealed a region where charged particles behave differently and where the sun's influence fades into the general background of the galaxy. The change was not a cliff, but a transition measured by shifts in counts and fields. It confirmed that our star's breath creates a bubble that shields us from some of the harshness outside. There is comfort in knowing that small objects can slip quietly into the wider dark and carry news in simple beeps. Persistence and patience make distance manageable. 42. A photon travels weightless yet shapes gravity's story. Light has no rest mass, but it carries energy and momentum. In the book of gravity, energy and momentum are the entries that matter, so light contributes to curvature, even as it rides along curves laid down by other sources. Near a heavy body, a beam bends and takes longer to pass than it would in a flatter region. The effect is small near a planet and strong near a black hole. In extreme environments, light can orbit for a brief time along a precarious path, circling at a radius where any nudge inward drags it down and any nudge outward lets it escape. Images of black hole shadows trace the last safe orbits of photons, creating rings that encode the mass and spin of the central object. The dance of weightless travelers reveals the strength of the stage. On cosmological scales, the energy stored in background radiation once dominated the dynamics of the universe. As expansion stretched the light and diluted its pressure, matter took over the lead, and later the energy of empty space rose to prominence. The baton has changed hands more than once in this long performance. The story is gentle despite its grandeur. Even what seems intangible can influence the shape of events. A whisper of light can curve a path, and a path can guide a whisper to where it will be heard. 43. Space has a pressure that can push a sail. Photons reflect from a bright surface and transfer a tiny impulse. Over time and distance, countless such minuscule taps add up to a steady push. Engineers turn this into motion with solar sails, wide and light films that catch sunlight and turn it into thrust without fuel. Trajectories become slow spirals outward, and missions become exercises in patience and precision. The push is not limited to sunlight. The glow of a star can herd dust into patterns within rings around young systems. The background radiation of the universe exerts its own pressure, vanishingly faint yet real. In the earliest times, this pressure shaped the growth of structures by resisting collapse until enough mass gathered. Sailing by light requires new habits of navigation. There is no burn and coast. There is only continuous gentle force that can be aimed by tilting the sail. Small adjustments now become large effects later. The craft moves without the hiss of reaction mass, like a boat riding a current with a steady breeze. As an image for rest, this is useful. Effort does not have to be abrupt to produce change. A tiny consistent push in a calm direction carries you far. 44. The sun's light takes 8 minutes to reach you. The glow that warms skin and feeds leaves began in the core of a star where hydrogen fuses into helium. Energy there begins a slow diffusion outward, bouncing among particles for thousands to millions of years before it reaches the surface. Once free, photons cross the gap to Earth in about 500 seconds, sprinting through space with no obstacles but geometry. This delay creates a small temporal distance between source and experience. If the sun could vanish, which physics forbids, daylight would still bathe Earth for those minutes. The same lag applies to every view outward. What is seen is always a little late, and the farther the object, the older the news. Seeing is a form of time travel within safe limits. Knowing the path of this light is part of knowing the stability of life here. The sun's output varies on cycles that touch the ionosphere and polar skies, yet remains steady enough to allow climates and ecosystems to persist. The balance is not perfect, and seasons bring change, but the average remains patient and supportive. A calm thought follows. Daily warmth is the end of a journey that began long before any plan. Reliable gifts can have long beginnings. 45. The moon slowly drifts away from Earth. Tides raised by the moon in Earth's oceans drag a little against the rotation of the planet, transferring energy that nudges the moon outward by a few centimeters each year. Ancient rocks record longer days in the past, and precise laser reflections from mirrors left on the lunar surface confirm the current retreat. The dance of two bodies evolves in tiny steps that add up over deep time. This drift changes more than distance. It alters the length of a month, the timing of eclipses, and the small oscillations that the moon's gravity induces in Earth's spin. The system remains stable, but the parameters slide slowly, offering a quiet reminder that even familiar companions do not hold perfectly still. Stability is a dynamic agreement, not a frozen pose. The tides that cause the drift also shape coastlines, feed estuaries, and stir nutrients that sustain life. The exchange of energy threads through weather, biology, and geology, binding seas and skies to the pull of the satellite overhead. A faint connection becomes a broad influence when multiplied by years beyond counting. 46. Jupiter's magnetic field is a giant invisible shield. The largest planet in the solar system spins rapidly and carries a magnetic field 14 times stronger than Earth's. This immense magnetosphere balloons outward millions of kilometers, deflecting charged particles from the sun and trapping others in swirling belts of radiation. Moons such as Io and Europa orbit within this dynamic environment, their surfaces and atmospheres continually shaped by it. The field arises from electric currents in metallic hydrogen deep inside Jupiter's vast interior. Rotation whips those currents into loops, generating magnetic lines that twist and pulse. At the poles, particles following the field lines crash into the atmosphere and create auroras so powerful they could outshine all other planetary auroras combined. Telescopes see them glowing in ultraviolet light like silent storms. For spacecraft passing nearby, the field is both a challenge and a protection. Instruments must be shielded against radiation while they record the field's rhythm. Measurements from missions like Juno reveal complex layers and surprising asymmetries, showing that the magnetosphere breathes with the planet's rotation and with the gusts of solar wind. Thinking of Jupiter at night is thinking of calm strength. It guards its moons, holds its shape, and turns endlessly, a quiet sentinel whose unseen influence keeps order in the outer reaches of the solar family. 47. The Milky Way carries spiral arms like a storm. Seen from outside, our galaxy would appear as a graceful swirl of stars and dust, a pattern formed by waves of density moving through the disk. These spiral arms are not rigid structures, but zones where material bunches up as it orbits, triggering star formation that outlines the pattern in bright young clusters and nebulae. Between arms, older stars glide in relative quiet. Rotation balances gravity so that stars complete circuits in hundreds of millions of years, maintaining the general spiral form while details shift. Radio maps of hydrogen, attunement in infrared, views through dust, reveal that the Milky Way hosts several major arms and smaller spurs linking them like bridges in a river delta. Our sun is near the edge of one minor arm, a peaceful suburb of a busy city. The spiral pattern helps trace the flow of matter and energy. Shock fronts where gas compresses create stellar nurseries. Supernova explosions then inject energy that stirs and recycles the medium, feeding the next wave. The result is an ecosystem of light, perpetually renewing itself over galactic timescales. To picture this from a quiet room is to sense rotation as harmony. Everything moves, but motion has design. What seems chaotic from up close becomes a pattern from far away. That perspective eases the mind towards stillness. 48. Cosmic dust seeds new stars and planets. Tiny grains of silicate, carbon and ice drift through space, leftovers from dying stars and the collisions of asteroids. Each grain is smaller than a strand of smoke, yet vital to the life cycle of galaxies. Dust absorbs starlight, cools gas clouds, and provides surfaces where molecules can form. Without it, clouds would stay too warm to collapse, and the chemistry of life would lack a starting point. In stellar nurseries, dust gathers with gas into dense nuggets. Gravity squeezes them until heat and pressure ignite new stars. Around those stars, leftover dust forms disks where particles stick together, building pebbles, rocks, and eventually worlds. Microscopic motes thus become continents and oceans after eons of quiet accumulation. Observations with infrared and millimeter telescopes capture these processes in detail. Rings, gaps, and spirals in young disks reveal where planets are already sculpting their surroundings. Spectra show the fingerprints of water, organics, and silicates, ingredients of future landscapes. From simplicity grows structure, from faint haze emerges solidity. There is peace in knowing that creation can proceed grain by grain. Progress need not be loud. A drifting speck can start a chain that ends in sunlight on skin or rain on soil. 49. The universe might have more dimensions than we sense. We move through 3 of space and 1 of time, yet mathematical frameworks that unify gravity with quantum physics often require extra dimensions curled too small to notice. These hidden directions could influence the strengths of forces and the behavior of particles without ever revealing themselves directly. They would be like folded threads in the fabric of reality, subtle but essential to the pattern. The concept arose in attempts to reconcile general relativity with quantum field theory, where forces appear as vibrations of extended entities rather than points. In such models, geometry is not merely backdrop but participant, with properties of space determining which kinds of particles can exist. The extra dimensions provide room for that geometry to express all observed symmetries. Experiments search for indirect signs, deviations in gravitational strength at tiny scales, energy missing from collisions that might slip into unseen directions, patterns in cosmic radiation that hint at hidden topology. So far, nature keeps her answer quiet, offering neither confirmation nor denial. The mystery remains dignified, unhurried. Whether or not extra dimensions exist, the thought broadens imagination. The world may be richer than perception allows. Accepting that possibility is its own kind of expansion, an inner spaciousness mirroring the outer one. 50. The expansion of the universe is accelerating. Astronomers once expected gravity to slow cosmic growth, but observations of distant supernovae revealed the opposite. Galaxies are drifting apart faster over time. Something pervasive, called dark energy, appears to push on space itself, adding momentum to the expansion. Its exact nature is still unknown, yet its effect is unmistakable in the data. This discovery reshaped modern cosmology. Equations that once predicted a steady deceleration had to include a term for this mysterious pressure. Surveys of galaxy clusters, gravitational lenses, and the cosmic microwave background all confirm the same conclusion. The universe's fabric is stretching with increasing ease. The balance between attraction and repulsion has tilted toward openness. On practical timescales, this change is gentle, altering nothing in daily life. But on cosmic scales it will define the far future, slowly dimming the view as distant galaxies move beyond visibility. The cosmos will not end with a bang but with separation and silence, a slow fade into isolation that nevertheless preserves structure locally. Contemplating acceleration invites calm rather than fear. Expansion is part of the design, not a disaster. Even in growth without end, there is symmetry, a reminder that stillness and motion can coexist when viewed from the right distance. 51. Some quasars outshine entire galaxies. In the far reaches of space, astronomers have found objects so bright that they can be seen across billions of light years. These are quasars, the blazing hearts of galaxies powered by supermassive black holes feeding on gas and dust. As matter falls inward, friction heats it to extreme temperatures, and magnetic fields launch jets of particles near light speed. The energy released can eclipse the combined output of hundreds of billions of stars. Quasars are more than spectacles, they are beacons from the universe's youth. Most shone when galaxies were still forming, providing records of early cosmic conditions. Their light travels through clouds of intergalactic gas, imprinting absorption lines that reveal the composition and temperature of space along the way. Each quasar therefore acts as both lamp and messenger, illuminating what lies between. Observations show that as black holes consume their surroundings, they also influence them. Radiation and winds from quasars can blow away gas, halting further star formation for a time and regulating the growth of their host galaxies. This feedback turns violent feeding into eventual balance, an elegant mechanism hidden behind apparent chaos. To imagine such power while resting is to grasp scale without agitation. Violence on that magnitude produces harmony across time. Outbursts that seem destructive serve the continuity of the larger design. 52. the center of our galaxy whispers in radio. At the heart of the Milky Way, beyond dense veils of dust, lies a compact source known as Sagittarius, a star. It is a supermassive black hole about 4 million times the mass of the Sun, silent in visible light but murmuring in radio waves and X-rays. These emissions flicker as clumps of gas spiral inward, tracing magnetic lines and shocks in the hot plasma near the event horizon. Radio telescopes link across continents to create an Earth-sized dish that can resolve details near that horizon. The resulting images show a faint ring of emission surrounding a dark shadow where light cannot escape. That shadow is the outline of space-time itself under gravity's full strength. Each pixel on those images condenses years of coordination among stations separated by oceans. The radio center also serves as a marker for mapping the galaxy. By measuring motions of nearby stars and gas clouds around it, astronomers derive the mass of the black hole and confirm general relativity and strong fields. The precision of those orbits is astonishing, celestial choreography written in pure geometry. Listening to that whisper at night is a tranquil act. It reminds us that even the most powerful engines can hum softly, that the core of a galaxy can speak in low frequencies instead of thunder. 53. The cosmic background hum still echoes creation. Every direction of the sky carries a faint microwave glow, a relic from when the universe was about 380,000 years old. Its temperature is just under 3 degrees above absolute zero. But sensitive instruments record minute variations, ripples less than 1 part in 100,000 that map the first seeds of structure. These ripples are the aftertaste of the moment when light was first free to travel. This background hum provides the foundation for cosmology. By studying its patterns, scientists infer the age, composition, and geometry of the universe. The agreement between independent measurements is one of the great achievements of modern science, showing that an event billions of years past still writes its signature across today's sky. Despite its origin in heat and chaos, the background is calm, smooth, and almost uniform. Its slight imperfections are precisely what allowed galaxies and stars to form. Without them, matter would never have gathered. Imperfection, it turns out, was the seed of beauty. To listen to that hum in imagination is to hear the oldest lullaby. The universe has been singing softly for nearly 14 billion years, and the song has never stopped. 54. Massive stars live fast and end brilliantly. Stars much larger than the Sun burn through their fuel in only a few million years, their cores reaching temperatures that fuse heavy elements and release torrents of energy. As pressure mounts, they shine with fierce intensity, but their brightness is short-lived. When the core fuel is gone, equilibrium breaks and gravity collapses the star, triggering an explosion that can outshine a whole galaxy for weeks. These supernovae are cosmic recyclers. Their blast waves spread elements such as carbon, oxygen, calcium, and iron into surrounding space, enriching future generations of stars and planets. Without such violent endings, the building blocks of life would remain locked inside stellar hearts forever. The remnants of these explosions take different forms depending on mass. Neutron stars for the moderately massive, black holes for the heaviest. The debris fields become colourful nebulae, expanding shells of gas that glow for tens of thousands of years. The Crab Nebula is one such relic, a reminder that destruction and creation share the same moment. The brief, brilliant lives of massive stars teach serenity rather than urgency. Even the most intense fire contributes to balance. Energy released in seconds sustains beauty for eons, showing that purpose does not depend on duration. 55. Starbirth nurseries glow behind veils of dust. Within spiral arms and molecular clouds, knots of gas collapse under gravity, forming protostars wrapped in cocoons of dust. As they heat up, their radiation pushes on the surrounding material, carving out cavities and sending jets of gas into space. Infrared telescopes peer through the obscuring dust to reveal these hidden realms, where light and shadow alternate in slow motion. Such regions are vast yet delicate. A single cloud can contain the mass of thousands of suns, but its density is so low that an airplane flying through it would not notice. Over millions of years, turbulence and magnetic fields guide the birth of clusters of stars, each with its own potential system of planets. The interplay of forces resembles a sculptor's hand shaping clay too hot and fragile to touch. Star-forming regions emit a characteristic glow from ionized hydrogen, creating the pinkish hues seen in images of the Orion Nebula or the Carina Nebula. These colors, invisible to the naked eye, are brought into view by long exposures that translate energy into vision. What looks chaotic is in fact balanced motion within a self-regulating ecosystem. Thinking of these nurseries while drifting to sleep can steady the heart. Creation proceeds quietly behind curtains, needing only time, gravity, and patience, qualities available even to a resting mind. 56. Brown dwarfs are failed stars that still glow. Not every object born in a gas cloud gains enough mass to ignite sustained hydrogen fusion. Some stop just short, glowing dimly from residual heat and the fusion of heavier isotopes like deuterium. These brown dwarfs bridge the gap between planets and stars, invisible to the eye but detectable in infrared as faint embers scattered through space. Their atmospheres contain clouds of metal oxides and silicates, giving rise to exotic weather patterns. Some show temperature stripes and storms reminiscent of giant planets, while others cool to temperatures where iron and mineral rain may fall. Despite their muted light, they contribute significantly to the galaxy's mass and provide laboratories for studying the physics of atmospheres and magnetism. Brown dwarfs often travel with companions, stars or planets, or drift alone through interstellar space. Because they cool slowly, they can persist for billions of years, silent and enduring witnesses to galactic history. They are neither fully alive as stars nor truly inert as rocks, occupying a serene middle ground. Contemplating them encourages acceptance of in-between states. Existence need not be brilliant to be meaningful. Even quiet warmth is a form of light. 57. Black holes may evaporate over unimaginable times. Stephen Hawking's theory of quantum radiation predicts that black holes are not completely black. Tiny fluctuations near the event horizon can allow pairs of virtual particles to separate, with one escaping as radiation and the other falling in, slowly reducing the black hole's mass. The process is so slow that for stellar mass black holes it would take far longer than the current age of the universe to complete. As the black hole shrinks, the radiation increases in intensity, leading eventually to a final burst that releases the last of its energy. No one has observed this evaporation directly, it remains a theoretical whisper, but it unites the physics of gravity, quantum fields, and thermodynamics in an elegant framework that hints at deeper connections yet to be discovered. If true, the idea suggests that even the most permanent-seeming objects participate in cycles of change. Nothing endures forever, not even space-time's most secret vaults. The universe balances accumulation with release, gravity with radiation, silence with a faint hiss of energy. This understanding can bring calm. Endings are not abrupt erasures but slow dissolutions, graceful and complete. Even darkness has a way to return its energy to the light. 58. The ultimate fate could be a long, cold fading. If dark energy continues to drive acceleration, galaxies will drift apart faster than light can bridge the gaps between them. Star formation will dwindle as fuel is used up, leaving old stars to burn out one by one. Black holes will evaporate over unimaginable spans, and the universe will settle into a thin bath of photons and particles at near absolute zero. It will not end in fire but in frost. This scenario, often called heat death, is not a tragedy. It is a projection of balance carried to its quiet conclusion. Energy spreads evenly, gradients vanish, and the capacity for work ceases. In that distant era, time itself may lose meaning because nothing will change. The universe will become a perfectly calm sea. Other possibilities exist as cyclic rebirths, quantum bounces, new inflations, but all share the idea that stillness follows activity. The story closes gently, without spectacle, as entropy completes its ascent. Each step along the way, from stars to galaxies to atoms, contributes to the same movement toward equilibrium. Thinking of that end invites neither fear nor urgency. It teaches rest. If the cosmos itself will one day exhale and settle, then rest is part of the plan, not a pause in it. Vastness. The shape of the universe can curve subtly. Geometry in cosmology is not abstract. It decides how parallel lines behave and how light travels. A positive curvature would make space close on itself, like the surface of a sphere, while a negative curvature would make it open like a saddle. Measurements of the cosmic microwave background suggest that curvature, if it exists, is small, so small that space appears nearly flat across the observable region. To test curvature, scientists compare the apparent sizes of distant features with predictions from different geometries. The precision required is extraordinary, involving millions of galaxies and sensitive satellite data. The current consensus leans toward flatness, but leaves room for a whisper of curve, a gentle reminder that perfection may never be exact. Curvature influences destiny. A closed universe might eventually slow and collapse, while an open one expands forever. The difference rests on fractions of a percent in density and energy. The fine balance reveals how delicately the cosmos sits between competing tendencies. The concept offers quiet reassurance. Even on the larger scales, the difference between falling back and drifting onward can be minute. Existence itself seems tuned for continuation. 6D, magnetic fields thread galaxies with order. Every galaxy carries vast magnetic structures intertwined with its gas and dust. Though invisible, these fields guide charged particles, shape the paths of cosmic rays, and influence how gas clouds collapse into stars. Radio observations reveal their spiraling patterns following galactic arms, while polarized light from dust grains maps their orientation in glowing filaments. The origin of such cosmic magnetism likely lies in small seed fields amplified by motion and rotation over billions of years. Dynamos powered by turbulence and differential spin strengthen and maintain them, converting kinetic energy into magnetic structure. The result is a vast invisible architecture that gives coherence to otherwise chaotic motion. These fields connect local scales to cosmic ones, from the Sun's own magnetic cycles to the loops stretching across clusters of galaxies. They are the silent weavers of continuity, linking plasma, radiation, and matter in delicate balance. As an image for reflection, imagine every thought as a small field threading your day. Most remain unseen, yet they shape motion and mood. Invisible order is still order, and it endures. 61. Planetary systems form from swirling disks. Around newborn stars, the leftover gas and dust gather into thin, rotating disks. Within these disks, grains collide, stick, and grow as the material gradually cools. Over time, small clusters become planetesimals, planetesimals become embryos, and embryos merge into planets. The process is gentle yet inevitable, guided by gravity, friction, and the quiet persistence of motion. Observations of young stars across the galaxy confirm this pattern. Telescopes like ALMA and James Webb reveal rings, gaps, and spirals in these dusty disks, signatures of planets in the making. The same structures once surrounded our own sun billions of years ago, long before Earth had oceans or a sky. Every pebble and every breath of the gas in those ancient swirls contributed to the world that now reads the stars. Not all disks form the same way. Some lose gas quickly and create rocky systems, others retain thick atmospheres that yield giants like Jupiter. Magnetism, turbulence, and the timing of star formation all play roles. Nature's creativity is tireless, exploring variations with no repetition yet no waste. Thinking of such quiet assembly brings peace. Worlds are not thrown together by chaos but shaped by patience. Even disorder can lead to elegance when time is allowed to work without interruption. 62. Tidal forces stretch moons and heat their cores. When a moon orbits close to its planet, the difference in gravity between its near and far sides creates tides not just in its oceans but in its solid body. The continual flexing releases heat through friction, sometimes enough to melt ice and rock beneath the surface. This hidden warmth can sustain volcanoes or subsurface seas long after sunlight fades. Jupiter's moon Io is the most volcanic body known, its surface constantly renewed by eruptions powered by tides. Europa, another Jovian moon, hides a global ocean beneath its icy shell, kept liquid by the same mechanism. Even distant Enceladus around Saturn sends plumes of water vapor into space, evidence of warmth maintained by gentle cosmic kneading. Tidal heating shows how motion can replace sunlight as a source of energy. Life, if it exists in those oceans, would live in eternal night, but not in cold. Hydrothermal vents on Earth's seafloor provide a possible analogy, places where chemistry and heat meet to build complexity from simplicity. The principle is comforting. Pressure and strain endured without breaking can generate life's warmth. Energy can arise from resistance, and stability can hide a pulsing heart beneath its surface. 63. Ice worlds may hide warm oceans. Far from the sun, where light is weak and temperatures plunge, several moons and dwarf planets conceal oceans beneath crusts of ice. Europa, Enceladus, Titan, and even distant Pluto show hints of liquid water locked inside, warmed by internal heat and tidal motion. These secret seas could be the most widespread habitats in the solar system. Probes and telescopes gather indirect clues: magnetic fields that vary with time, geysers of vapor escaping through cracks, and smooth surfaces that suggest renewal. Each discovery strengthens the idea that water, the medium of life, persists even in darkness. Where there is water and energy, chemistry can organize itself in surprising ways. The notion transforms the map of potential life. Instead of a single narrow zone around stars, habitability may exist wherever energy and water meet, even under kilometers of ice. Future missions plan to drill, fly through plumes, or send orbiters to sample these alien oceans and test the whispers of biology. It is soothing to imagine such quiet, hidden worlds. They lie in perpetual twilight, calm and untouched, carrying their secrets in layers that glisten faintly under the gaze of distant sunlight. 64 comets deliver ancient ingredients to young worlds. Comets are time capsules from the dawn of the solar system, icy remnants preserved in the cold outer regions until gravity sends them inward. As they near the sun, they warm, release gas and dust, and develop glowing tails that trace their paths. The material they shed contains water, organics, and complex molecules, ingredients essential for life. When comets strike or graze young planets, they deliver those compounds, enriching barren surfaces with chemistry that can evolve further. Analyses of comet samples and spectra reveal amino acids, sugars, and other precursors of biology. Earth's oceans may owe part of their water to such ancient messengers, mixed with contributions from asteroids and volcanic outgassing. Each comet's orbit is unique, some returning every few years, others visiting once in millions. Their trajectories link the solar system's past with its present, reminders of the chaos and generosity of formation. Even as they disintegrate, they seed meteor showers that mark seasons in the sky. There is calm in this continuity. Life owes something to fleeting visitors made of ice and dust. Transience itself can be fertile, leaving traces that endure long after the traveller is gone. 65. The sun is a quiet fusion engine. Beneath its shining surface, the sun converts about 4 million tons of matter into energy every second, yet it does so with remarkable stability. The fusion of hydrogen into helium proceeds in a slow, balanced chain, releasing light and heat that spread through space to sustain life on Earth. Each photon that reaches us began its journey inside atomic collisions that obey the same laws as a candle's flame, scaled to cosmic dimensions. Pressure and gravity maintain equilibrium. If the core's fusion slows, the sun contracts slightly, increasing temperature and restoring balance. If it accelerates, the core expands and cools. This self-regulation has kept the sun steady for billions of years and will continue for billions more. Its calmness is not absence of power, it is mastery of it. The light that leaves the surface takes only 8 minutes to reach Earth, but the energy's journey through the dense interior may have lasted hundreds of thousands of years. By the time it arrives, it is diffused, softened and safe, transformed from violent nuclear reactions into nurturing warmth. Thinking of the sun this way encourages faith in steady processes. True strength need not erupt, it can hum for years, reliable and serene. 66. Aurora. Paint polar skies with solar breath. Charged particles from the solar wind follow Earth's magnetic field toward the poles, where they collide with atoms in the upper atmosphere. Those collisions release light, greens from oxygen, purples and reds from nitrogen, creating shimmering curtains that wave across the night. The display is silent but powerful, a visible dialogue between star and planet. The patterns vary with solar activity. During strong storms, aurorae expand toward lower latitudes, forming crowns of light that ripple and shift in seconds. Satellites detect the accompanying bursts of energy that can disturb radio and power systems, reminding us that beauty and force often share the same origin. Each display begins 150 kilometers above ground, yet feels intimate, as if the sky were breathing in color. Photographers chase them across frozen lakes, while indigenous cultures have woven them into myths for centuries. Science adds measurement without stealing wonder, explaining the dance without ending it. As you drift towards sleep, picture those lights flowing overhead. They are proof that even invisible winds can create art, and that contact between worlds need not be violent to be sublime. 67. The night sky you see slowly changes over ages. The constellations that seem eternal are temporary alignments. Stars move through the galaxy at different speeds and directions, and over tens of thousands of years, their patterns warp and rearrange. Future skies will display unfamiliar figures, while ancient humans saw shapes slightly different from ours. The firmament is a slow kaleidoscope. Proper motion measurements record these gradual drifts, allowing astronomers to predict how constellations will look in the distant epochs. Simulations show Orion stretching apart, the Big Dipper dissolving, and new forms emerging from current neighbours. The dance is subtle on human timescales but unstoppable on cosmic ones. Beneath that movement lies the rotation of the Milky Way itself. Our Sun circles the galactic centre once every 230 million years, carrying its planets through shifting tides of interstellar dust and gas. The familiar night canopy is just one frame in that immense journey. Knowing this can make the sky even more comforting. Change is universal, but it happens with grace. Stars keep their appointments even as they drift, and the rhythm of their motion mirrors the patience life requires. 68. Some stars orbit each other for billions of years. Binary and multiple star systems are common throughout the galaxy. Two stars locked in mutual gravity trace elegant ellipses around a shared centre of mass, their light rising and falling as they eclipse or move apart. Some pairs are so close they share material. Others are separated by vast distances yet remain bound. Together they age, evolve, and sometimes end their lives entwined. These unions influence stellar evolution. Mass transfer from one star to another can spark novae or reshape lifetimes, while mergers can create unusual giants or trigger bursts of radiation. Even stable pairs slowly exchange energy, each keeping the other's orbit honest through the pull of attraction. Observing binaries provides key measurements for astrophysics. From their motions we calculate masses, distances, and internal processes that single stars alone could not reveal. The principles of balance and reciprocity underlie both their mechanics and their metaphor. In the quiet of night, imagining such partnerships is soothing. Gravity binds without chains, allowing freedom within connection. Two lights circling each other for eternity show how cooperation can be eternal and effortless. 69. Stellar winds sculpt giant cosmic bubbles. Massive stars shed material in steady outflows that stream outward at hundreds of kilometers per second. These stellar winds collide with surrounding gas, sweeping it into expanding shells that glow in ultraviolet and X-ray light. When multiple stars in a cluster contribute their winds, the combined effect hollows out vast cavities in the interstellar medium, bordered by gibbous ridges of compressed dust and gas. As the winds meet resistance, shock fronts form, heating gas to millions of degrees and triggering new waves of star formation along the edges. The process is both destructive and creative, recycling material into new generations. Over time, these bubbles merge and overlap, creating the textured landscape of a galaxy's disk, a pattern of hollows and walls where light and matter play hide and seek. Astronomers map these structures to understand how energy flows from stars back into their environment. The feedback regulates how galaxies evolve, ensuring that star birth and death remain balanced rather than run away. Each bubble is a pause between breaths in a vast respiratory system. 70. Dark matter outweighs visible matter by far. What we see, the stars, gas and glowing dust, accounts for only a small fraction of all matter in the universe. The rest is dark matter, unseen but detectable through its gravitational pull. Galaxies spin too quickly for their visible mass alone to hold them together, and clusters of galaxies bend light more than their brightness would allow. Something invisible provides the missing gravity, shaping the skeleton of the cosmos. Despite decades of study, dark matter has never been observed directly. Experiments deep underground and in orbit wait for rare collisions between dark matter particles and ordinary atoms, but so far the silence endures. Theories propose candidates ranging from weakly interacting particles to exotic actions, or even compact objects from the early universe. Each possibility invites new designs of detectors and new patience. Simulations using dark matter reproduce the web-like distribution of galaxies we observe. Without it, structure would not have formed quickly enough after the Big Bang. It acts as the unseen scaffolding around which visible matter gathers, guiding evolution with a steady, silent hand. Its invisibility does not make it absent. It simply reminds us that reality is larger than perception. the idea carries a quiet lesson. The most influential forces often work in shadows. The hidden can hold the world together just as surely as what shines. 71. Dark energy dominates the cosmic budget. While dark matter binds galaxies, dark energy drives them apart. It fills space uniformly and exerts a pressure that accelerates expansion. Observations of distant supernovae and the cosmic background radiation indicate that about 70% of the universe's total energy resides in this mysterious form. It does not cluster, it does not emit light, and it may be an intrinsic property of space itself. Physicists describe dark energy through a parameter known as the cosmological constant, yet whether it is truly constant or slowly changing remains uncertain. Some models tie it to quantum fluctuations of the vacuum, others to new fields that evolve over time. Whatever its source, its influence is measured by the way galaxies drift farther apart and by the subtle imprint it leaves on cosmic structures. If dark energy continues unchanged, expansion will accelerate indefinitely. Over trillions of years, distant galaxies will fade from view, and the observable universe will shrink to our local group of stars. In that far future, the night sky will be mostly empty, though calm and stable. Some systems find harmony after turbulence, settling into patterns that endure for billions of years. Migration affects everything else: the delivery of water to rocky planets, the shape of asteroid belts, and the potential for life. Earth's own history may owe its gentle climate to the stabilizing influence of Jupiter's gradual movements in the past. A planet's path, like a life's, can change without destroying its purpose. This cosmic wandering shows that displacement can lead to balance. Change of position can preserve the system, not ruin it. 76 Urus. Neonatal stars shoot jets into space. Young stars often reveal their presence by sending narrow streams of gas outward at hundreds of kilometers per second. These bipolar jets pierce surrounding clouds, glowing where they collide with interstellar material. The symmetry of these beams comes from magnetic fields that channel rotating disks of gas into focused flows, converting angular momentum into beauty. As jets clear cavities through their birth clouds, they allow starlight to escape and mark the end of formation. Observations in visible and infrared light show shock fronts, called Herbig-Haro objects, that line up along the jets like beads, each representing an episode of renewed activity. The sequence captures years of cosmic adolescence, restless but creative. Jets play an essential role in regulating growth. By carrying away excess spin and energy, they let the central protostar settle into equilibrium. Without them, collapse might continue uncontrollably. Balance arises not from stillness but from controlled release. Each jet is a bridge between violence and grace, a reminder that the road to maturity involves expression as well as containment. Energy guided by the structure, where it becomes art of 77. Supermassive black cushion holes regulate galaxy growth. At the center of most galaxies, including our own, lies a black hole millions to billions of times the mass of the Sun. When gas falls toward it, energy released in radiation and jets can heat and disperse the surrounding material, halting further star formation. When the feeding subsides, the environment cools and new stars can form again. The cycle repeats, preventing galaxies from growing unchecked. This feedback connects the smallest and largest scales. Events near an event horizon influence systems spanning hundreds of thousands of light years. Observations reveal tight correlations between black hole mass and the properties of the host galaxy's central bulge, suggesting that both evolve together. They are partners in a slow gravitational duet. High-energy emissions from active galactic nuclei, powered by these central engines, shape intergalactic space, enriching it with elements and magnetic fields. Over cosmic time, such outflows set the conditions for the next generation of galaxies, making black holes paradoxically creative through their restraint. The message is subtle but clear. Power finds equilibrium in feedback, not excess. The universe keeps order not by forbidding growth, but by tempering it with wisdom, built into physics itself. 78. Cosmic background neutrinos are everywhere. Alongside the familiar cosmic microwave background exists an even older relic, a sea of neutrinos released seconds after the Big Bang. These ghostly particles, almost without mass and nearly impossible to detect, pervade the cosmos at a density of hundreds per cubic centimeter. They pass through stars, planets, and bodies effortlessly. their presence known only through rare interactions. Evidence for this neutrino background comes indirectly from its effects on the formation of structures and the patterns in the cosmic microwave background. Experiments deep underground and in space seek its faint fingerprints, hoping to complete the picture of the universe's earliest moments. To catch even a whisper from this ancient ocean would be to hear a voice from the first heartbeat of time. Neutrinos also emerge from modern processes, nuclear reactions in stars, supernova explosions, and the radioactive decay of elements. They link the everyday to the cosmic, the fleeting to the eternal. Each one carries information about the event that birthed it and travels almost unaltered across the universe. Their omnipresence teaches humility. Most of reality moves unseen, silent and effortless, filling space with activity we can barely notice yet depend upon for balance. 79. The interstellar medium is a delicate blend of gas and dust. Between stars lies a thin mixture that forms the raw material for future generations of suns and planets. Though its density is lower than the best vacuum on Earth, its sheer volume makes it crucial in galactic ecology. Waves of pressure, radiation, and magnetic fields ripple through it, creating clouds, filaments, and voids in a ceaseless slow dance. This medium glows faintly in radio, infrared, and X-ray light depending on temperature and composition. Shock waves from supernovae compress it, stellar winds carve bubbles within it, gravity gathers it again into denser regions where new stars can be born. It is the bloodstream of a galaxy circulating matter and energy from death to rebirth. Studying the interstellar medium reveals how elements mix and how molecules form in space. Spectroscopy detects carbon monoxide, water vapor, and even complex organics within its coldest pockets. The chemistry there foreshadows the recipes that later flourish on worlds. Awareness of this unseen environment adds calm perspective. The spaces between things are not empty but active, holding potential. Absence itself is a kind of substance when viewed with patient eyes. 80. The cosmic distance ladder measures the deep past. To gauge how far away the stars and galaxies lie, astronomers build a chain of methods that overlap for calibration. Parallax measures nearby stars through their tiny shifts against the background as Earth orbits the Sun. Cepheid variables and supernovae serve as standard candles for greater ranges. Redshifts then extend the scale to the edge of the observable universe. Each rung of this distance ladder depends on the one below, linking geometry, physics, and observation into a coherent structure. Refining it has taken centuries of meticulous work, from the first telescopic angles to modern satellites like Gaia, that chart billions of stars with exquisite precision. The ladder turns light into measurement and measurement into history. Through it we learn not only how far away galaxies are, but also how fast the universe expands. Distances translate into times. The farther the object, the earlier the era we observe. The ladder is both a ruler and a timeline, connecting the present moment to the first spark of structure. 81. Standard candles guide our map of expansion. Certain celestial objects shine with predictable luminosity, allowing their apparent brightness to reveal distance. Cepheid variable stars, which pulse in a regular rhythm, and Type Ia supernovae, born from white dwarfs reaching a critical mass, are two of the most reliable. By comparing their true power with their observed glow, astronomers chart the scale of the cosmos like navigators reading lights across an endless sea. These cosmic beacons helped uncover one of the greatest discoveries in science: that the universe is not static but expanding. When their light is examined from remote galaxies, it appears dimmer and redder than expected, evidence of space stretching during its journey. Step by step, such comparisons built the first accurate measurements of how quickly galaxies recede, leading to the definition of the Hubble constant. Precision matters deeply here. Even small uncertainties ripple into disagreements about the age of the universe and the behavior of dark energy. Modern observatories now refine these measurements to extraordinary accuracy, linking distant explosions and pulsations into a single cosmic yardstick. The stars themselves have become instruments, speaking in rhythm and flash rather than gears and dials. Standard candles show that trust in repetition reveals truth. The universe writes consistency into its language, and by reading its steady lights, humanity has learned to measure both distance and destiny. 82. Spectra are fingerprints of the stars. When starlight is split into its rainbow of colours, it carries thin dark lines where atoms have absorbed specific wavelengths. Each element leaves a unique pattern. a spectral signature that reveals composition, temperature, pressure, and motion. Even across billions of light years, these lines remain, turning light into a code that can be read long after the source has faded. This method, spectroscopy, transforms observation into chemistry. It confirms that stars share the same ingredients as Earth and that the laws of physics hold across the universe. From the hydrogen lines in distant quasars to the calcium traces in ancient suns, the same rules apply, binding the cosmos into one continuous laboratory. Spectra also record motion through the Doppler effect. When a star moves toward us, its lines shift toward blue. When it recedes, they move toward red. By measuring those shifts, astronomers map orbits, rotation, and even winds on exoplanets light years away. The universe becomes not just visible, but audible in data, a harmony written in color instead of sound. In every beam of light lies a complete story. To study spectra is to read history written by atoms themselves. Calm, precise, and timeless. 83. Metallicity tells the tale of stellar generations. Astronomers call all elements heavier than helium metals, and the fraction of these in a star's makeup, its metallicity, acts as an indicator of age. The earliest stars contained almost none, forged from the universe's pristine hydrogen and helium, and later generations inherited the metals produced by those first stars, each cycle enriching the galaxy further. The more metals a star holds, the younger its lineage tends to be. Measuring metallicity reveals patterns of migration and formation. Stars with similar chemical fingerprints likely formed in the same region, even if they now lie far apart. Streams of such kin wander through the Milky Way, remnants of smaller galaxies consumed by ours. In their spectra lies a record of ancient mergers and quiet assimilation. High metallicity favours rocky planets, since elements like iron, silicon, and oxygen are the building blocks of solid worlds. The chemistry of a star thus influences the potential for life around it. From the ashes of prior generations rise environments ready for complexity and awareness. This cyclical enrichment shows the universe as a patient craftsman. With each repetition it adds detail, layering new possibilities atop the remnants of the old until light itself carries memory. 84. The Hubble constant measures today's expansion. The rate at which galaxies recede from one another defines the tempo of cosmic growth. Known as the Hubble constant, it quantifies how fast the universe expands per unit of distance. Two main approaches, the observation of supernovae and Cepheid variables nearby, and the analysis of the cosmic microwave background from the early universe, yield slightly different values, a puzzle that keeps cosmologists attentive. The discrepancy may hint at unknown physics, perhaps a subtle change in dark energy or new particles altering the early cosmos, or it may reflect unrecognized complexities in measurement. Either way, the dialogue between datasets shows science at its most alive, questioning, refining, never fully settled. For all practical understanding, the Hubble constant tells us that galaxies beyond the local group recede faster the farther away they are. It links distance directly to velocity, a simple linear truth that unfolds into the whole history of expansion. What began as a dim pattern in spectra has become a ruler that measures time itself. Its precision increases every decade, yet its essence stays serene. A single number summarizing the rhythm of everything. Expansion is the universe breathing, and the Hubble constant is its pulse. 85. The cosmic web looks like neurons at gigantic stardust. When simulations plot billions of particles under gravity, the emerging pattern resembles a vast brain. Filaments of matter linking dense nodes and surrounding immense empty voids. Galaxies lie along these threads like sparks along synapses, forming an intricate network that connects the entire observable universe. The resemblance to neural tissue is coincidence, yet it reveals a unity of form that crosses unimaginable scales. This structure grew from tiny fluctuations in the early universe, magnified by dark matter's pull. Over billions of years, those small differences became highways of galaxies and basins of emptiness. Observations from deep surveys now confirm that reality follows the same design predicted by computation. The visible cosmos behaves like a single self-organizing system. Close your eyes now and let the noise of the day dissolve into the quiet pulse of the cosmos. Every breath you take echoes the slow expansion of space itself. Steady, gentle, infinite. The same forces that shaped galaxies guide the rhythm of your heartbeat. The same particles that once burned inside stars now drift peacefully in your veins. There is nothing to chase, nothing to control. The universe is still creating, even in silence. You are part of that silence, a small luminous thought floating through its calm expanse. Let the light that built everything cradle you tonight, and sleep knowing that you already belong to the endless harmony of the stars. If you enjoyed this journey, don't forget to like the video, comment and subscribe to our channel. With your support, we can make this community of science and discovery even bigger. Share your ideas with us, because it's always more exciting to explore the unknown together. As Carl Sagan said, reality may be much stranger than we realize. Science is the most powerful way to understand that strangeness.